Of nonlinear partial differential equation. If the given partial differential equation is of the format f of pqz equals 0, or you can rewrite the given partial differential equation which is nonlinear in the format f of pqz equals 0. To get the complete solution, the first step will be put p equals a dz by du and q equals dz by du, where u equals ax plus y. Now solve the function f of a dz by du, comma dz by du, comma z equals 0. This is the same function f of pqz equals 0. We have just written p as a dz by du, q as dz by du, z is written as it is. Solving this function, we will get the desired complete solution. Look at an example. Solve z equals p square plus q square. We can rewrite this function in the form f of pqz equals 0. By writing this format, we are looking for RHS 0 and LHS, which is purely a function on p, q and z. Here we rewrite z equals p square plus q square as p square plus q square minus z equals 0, which is of the format f of pqz equals 0. Now we have to put p equals a dz by du and q equals dz by du, where u equals ax plus y. Next step will be to rewrite p as this expression, q as this expression. Using the transformation p equals a into dz by du and q equals dz by du, our equation 1 becomes this. Now we can take outside dz by du common from these two expressions. Here we have dz by du the whole square that can be taken common outside, and we are left out with a square plus 1. Z can be taken to the RHS. This is done for the ease of integration. When dz by du the whole square is written in the LHS and a square plus 1 is taken as denominator to the RHS, and you take square root on both sides, we obtain dz by du equals square root z upon square root a square plus 1. Here, to integrate, we will bring root z as the denominator in the LHS and du as the numerator to the RHS. Now, when you integrate this part with respect to variable z and this part with respect to variable u, you have integral dz by root z, which can be integrated using integral z raised to n equals z raised to n plus 1 upon n plus 1. Here n equals negative 1 by 2 because z raised to half appears in the denominator. After integration, z raised to n plus 1 upon n plus 1 becomes z raised to minus 1 by 2 plus 1 upon minus 1 by 2 plus 1. And in the RHS, integral du is u. We have 1 by root of a square plus 1 is a constant. And here we have a constant of integration. 1 minus 1 by 2 is positive 1 by 2. Therefore, this term becomes z raised to half upon 1 by 2, which can be written as 2 times root z. And we have u with the transformation ax plus y. We have started the solution using the assumption that u equals ax plus y. Therefore, we have to resubstitute u as ax plus y itself. Now, if you square both sides, you have 4z equals ax plus y the whole square upon a square plus 1 plus constant of integration. This is the expression which gives you the complete solution. The speciality of complete solution is that it involves as many arbitrary constants as the number of independent variables. Here, number of independent variables equals 2 because x and y are the independent variables. In the complete solution, you can see that the two independent variables x and y occur. Also, the arbitrary constants are a and c. The constant of integration, also another constant appears. Since number of constants equals number of variables, you can verify that this is the complete solution which we had desired.